All right, we're going to do the report sheet for experiment 11. All right, so it says to give the rate law from the previous experiment. So that is rate. Okay. All right, so that is rate is equal to K, concentration of I minus, concentration of S2O8 minus 2. All right, then the next problem is give the concentrations of the reactants after mixing. All right, so the bottle said 0.2 molar Ki. We used 5 mils of that 0.2 molar Ki, and we added the 3, 5, 5, and started the reaction with 5. Our total volume is 18. And when you do that math, you get for your Ki 0.056 molar. And for your S2O8, it was 0.1. We used 5. What is it now that the volume is 18? And that is 0.028 molar. All right, so now we have to convert our temperatures into Kelvin. So you have your data sheet, you have your 4 different temperatures, and you will have to then convert those into Kelvin. So the data sheet that I picked out for the first one had 2.2 degrees Celsius, so you add 273.15, and you have 1 decimal, 2 decimals. You give your answer to 1 decimal, and that is 275.4. All right, the next temperature was 16.3 degrees Celsius. You add 273.15 to that. Then you have your rounding with the 5 and nothing after it rule, and that gives you 289.4 Kelvin. And then the third temperature I had was 26.1 degrees Celsius. Add 273.15, and you get 299.2. And then the last temperature was 35.8. All right, you add your 273.15, round to the even number, you get 309.0 Kelvin. All right, so those are your 4 temperatures converted to Kelvin. All right, so now we get to reaction time. Well, that's just data. Put your time in seconds. And then, so 3 is just data. 4, we need the reaction rate, and rate is equal to the disappearance in the concentration of your S2O3 minus 2 over 2 delta T. All right, and so we need our concentration of the S2O3 minus 2 after mixing. All right, so the bottle says, so we're doing MV is equal to MV. The bottle of the S2O3 says 0.0059 molar, and we use 5 mils of that. What is the molarity now that we've mixed the 5, 5, 5, and 3, total 18 mils? All right, and so same as the last lab, experiment 10, it is 0.0016 molar. All right, and so when we find our rates, the reaction turns blue when the concentration of the S2O3 goes to 0. We build up the I minus or I3 minus, it reacts with the starch and turns blue. And so the rate is equal to the disappearance of the S2O3. So the final is 0 minus initial is the 0.0016 over 2 times the delta T. And so you bring down your times for those 4 to get those 4 answers. And so I'm going to plug into here the 4 times that are on my data sheet that I am using. 923 seconds, and then 370 seconds, 370 seconds. And then 194 seconds. And then 98 seconds. All right, because it is going to be faster as you increase your temperature. All right, so when I plug in my numbers, I have rate 1, 8.7 times 10 to the minus 7 molarity per second. For the second one, 2.2 times 10 to the minus 6 molarity per second. For the third one, 4.1 times 10 to the minus 6 molarity per second. And for the last one, it is 8.2 times 10 to the minus 6. All right, so those are the 4 rates that you get when you use this data. All right, so then the next says calculate the rate constant. So now we're going to calculate the rate constant. And so rate, again, we wrote this at the beginning, rate is equal to K, concentration, I minus concentration, S2O8. All right, and so we just plug in our numbers. So rate 1 was 8.7 times 10 to the minus 7 molarity per second. We're going to solve for the rate constant K, our I minus. We, after mixing, calculated that, 0.056 molar. And then the S2O8 after mixing, that is the 0.028 molar. All right, divide both sides by 0.056, divide both sides by 0.028, and you get K1 for the first temperature, the ice bath, and that's 5.5 times 10 to the minus 4. And this is a second order reaction, and you can figure out the units by dividing by molarity. Dividing by molarity, you have the second order units for the rate constant K, and that is 1 over molarity times seconds. So that is K1. All right, so to get K2, we plug that in. And so instead of the 8.7, we plug in the 2.2 times 10 to the minus 6. Everything else is the same. 0.056, we've never changed the concentration of the I minus. We've never changed the concentration of the S2O8. We only changed the temperature in this experiment. And so the second K value is 1.4 times 10 to the minus 3, 1 over molarity times seconds. Then we plug in the 4.1 times 10 to the minus 6 molarity per second. That is equal to K, 0.056 molar, 0.028 molar. So all we're doing is putting in our 4 different rates. Everything else is the same, and we solve for K all 4 times. So the third K value that we get is 2.6 times 10 to the minus 3. And then finally, we put in our 8.2 times 10 to the minus 6 molarity per second is K, and the 0.056 times the 0.028. And then our last K value is 5.2 times 10 to the minus 3. And that's 1 over molarity times seconds, 1 over molarity times seconds, second order rate constant. All right, so the constants are not constant because we are changing the temperature, so they should be different. As you increase the temperature, you increase the rate of reaction, and you increase your rate constant K. So they should be increasing with increasing temperature. All right, so then you have your chart to fill out. All right, so the first column, you simply write down your temperature conversions. All right, so I had in the first column 275.4 Kelvin, 289.4 Kelvin, 299.2 Kelvin, and 309.0 Kelvin. So you just recopy that data. Now you simply take your calculator and you take 1 divided by that number and put the number in the second column. All right, and so that is 3.631 times 10 to the minus 3, and that is Kelvin to the minus 1. And then the second one, when you invert that, you get a 3.455 times 10 to the minus 3, Kelvin to the minus 1. And then you have your 3.342 times 10 to the minus 3, Kelvin to the minus 1. And then the last one is a 3.236 times 10 to the minus 3, Kelvin to the minus 1. So all you're doing, again, to get that answer is taking 1 divided by 275.4. All right, then the next column is delta T. Again, you're just putting down your time in seconds that you had above, and then you're going to have the rate constant K. You're going to write that 4 times. All right, so then the last column is the ln of K. And so you're going to find the natural log of K. And so you have your 4K values, and you just take the natural log. All right, so let's fill in the chart here. All right, so we're filling in the chart. So my change of time, 923 seconds, 370 seconds, 194 seconds, and 98 seconds. Those were the times in my data sheet. And then the K, I calculated those above, just rewrite them. 5.5 times 10 to the minus 4, 1.4 times 10 to the minus 3, 2.6 times 10 to the minus 3, 5.2 times 10 to the minus 3. And now you're going to take the ln of that. So you're going to take the ln of 5.5 times 10 to the minus 4, and that's going to give you a negative 7.51. You're going to take the ln of the 1.4 times 10 to the minus 3, your rate constant K, and that is negative 6.57. Then you're going to take the ln of 2.6 times 10 to the minus 3, and you're going to get negative 5.95. You're going to take the ln of 5.2 times 10 to the minus 3. So you're taking the ln of your rate constant Ks, and that is a minus 5.26. All right, so then you get the question number 6 on your report sheet, which is the activation energy and the Arrhenius frequency factor. Well, at the beginning of the report sheet, you have to do a graph. So you attach your Arrhenius plot of the ln of K versus 1 over T. That's why we have those numbers in our table. All right, the graph must include a title and label the X and Y axis. On your graph, you have to show your calculations for the slope, the y-intercept, all right, and also the calculations for energy of activation. All of that has to be shown on your graph. All right, so we're going to make a graph. I'm not going to have graph paper to do that on, so you must turn your graph in on graph paper. If not, it will be graded harshly. All graphs must be on graph paper. All right, so you must have a title. All right, you have to have your axes labeled. So this is going to be your ln of K versus your 1 over T, which is in Kelvin to the minus 1. All right, so now you've got to figure out how to use most of your graph paper. All right, and so for your ln K values up here in your chart, you have your highest and your lowest, and so you'll want to subtract them. All right, so you have your highest number is a negative 5.26, and your lowest number is a negative 7.51. All right, so I would go a little bit lower than the minus 7, and so I like integers, so I'm going to say minus 8. And then I would go a little bit higher than my highest number, so I'm going to say minus 5. All right, so I want my scale to go from my lowest possible number, which is negative 7.51, but I'm going to say on my graph, I'm going to make it minus 8. And then it needs to go up to a negative 5.26. I'm going to go up higher than that. I'm going to go up to a negative 5. So I have my graph, all right, and so I know for my ln of k, down here I'm going to have my -8, and up here I'm going to have my -5, and you must go up by a consistent amount. So every block must mean a number and not a 0.2345. It needs to go up by, say, 0.1 or 0.05 or 0.2, something that is a consistent, and you can get the readings off of the graph. You have to be able to read the graph accurately. All right, so you have to go from your lowest number to your highest number, and you have to use most of your graph. And it has to go up by a consistent amount. You're going to do the same thing for your y-axis. All right, so we look at our 1 over k, 1 over t values. Again, they're up in your chart. All right, and so they are all times 10 to the minus 3, which is nice. All right, so our highest number is going to be at 3.6. All right, so I'm going to go up to, say, 3.7 times 10 to the minus 3 as my largest number. All right, so I'm going to go a little larger than my largest. I'm going to go a little smaller than my smallest. So my smallest is 3.236, and so I can go down to 3.2 times 10 to the minus 3. And so my two numbers, the highest number, 3.7, lowest number, 3.2, to fit my 4 data points on the graph. All right. And so I'm going to start with the smaller number, 3.2 to 3.7. So down here, I'm going to have my number 3.2, and here 3.7. So my graph paper is here. Again, it has to go up by a consistent amount. And you want the 3.2 to be where the start is. You want that to... the end doesn't have to be 3.7, but we don't want 3.7 right here or right here. We want it at least to be 3/4 of the way over, so that your graph uses up at least half of the graph paper. All right. And now down here, I don't like to write times 10 to the minus 3 100 times. So then down here, I write times 10 to the minus 3. So I can go with a 3.2, a 3.25, a 3.3, a 3 point, whatever you're going up by to get to your 3.7. All right, so then when I put my 4 points on my graph, here's where my points, I did actually graph it accurately, but don't have graph paper on this. So I'm going to show you what my graph looks like. There, and then another one there, and then another one here. All right, and so I have my 4 points. All right, so note that I'm using most of my graph paper. And then you're going to draw a straight line. You have to get a straight edge. You're going to have, this is not going to be straight because I don't have a straight edge. All right, and so you're going to draw a straight line. All right, notice my straight line doesn't go through any of my points. So this is data points. These are going to have some error. And you're going to draw the best straight line using those 4 points. So I have 2 of my points that are above my line and 2 of my points that are below my line. So this is the best straight line that I can draw given those 4 points. All right. So now you're going to have to pick a point. And the points you're going to pick are when you have a perfect number here off of your graph and a perfect number here. You are not going to use the points of your data, unless, of course, that goes right through your best straight line. All right, you're going to pick 2 points on this line, and you're going to pick points where you can read exactly what it is here and exactly what it is here. And so you have all your squares. You want to make sure that that is in an edge of a square so you can get that accurate spot and this accurate spot. Same thing here. This is going to be in a square. You want it to cross exactly on that spot. And then you will have the accurate number from your graph. And so you're going to have your x1, comma, y1, and you're going to have your x2, comma, y2. So you have your 2 points. So you're going to pick 2 points off of your graph. I guess it could be 2 of your points if you have perfect data and your straight line is going through all 4 points. I will be looking at that very, very clearly to make sure that you have made a consistent here and a consistent here. Data points should not be perfect. There is error in all of our data points. And so you would draw your best straight line using those 4 points, and it may not go through any of them. All right, so now we simply find a slope. So the slope is the rise, so y2 minus y1 over the run, x2 minus x1. So that's how you get your slope. You simply take your points, you subtract your y's, you subtract your x's, and now you have your slope. All right, and now the equation is the ln of k, that's your y, is equal to negative energy of activation over r, 1 over t, that's your x, plus the ln of a. Now the a is the Arrhenius frequency factor. All right, so this is in the form of y is equal to mx plus b. We have graphed on the y-axis, ln k, on the x-axis, 1 over t. And so now we have our slope. We put in those numbers, and we have a slope. And so now we know that the slope is equal to the negative energy of activation over r. We also see that I have a graph, and your graph should look very similar to this. It's going to have a negative slope. And so the slope that you're going to get, as you see in this picture, is going to be a negative slope. And so your energy of activation is equal to, now your R value here, energy of activation has to be in joules per mole. So the R value is the 8.314 joules per mole Kelvin. And so your energy of activation is equal to your slope, which is going to be a negative number. All right. And so there's a negative out in front. That's where this negative is. All right. So a negative times a negative, energy of activation is always a positive number times the 8.314. That is your R value. So that's how you're going to get your energy of activation. You're going to get your slope. It's going to be negative. And then negative times a negative, that gives you a positive. And so you're simply going to take your slope times -1, which then makes it positive, times 8.314, which gives it the units of joules per mole. All right, and so then you have your energy of activation. Whatever you get, joules per mole. All right, so that has to be on your graph. That has to be on your graph. We have a point and a slope. If you have a point and a slope, you can then solve for the y-intercept. And so you pick a point. So you can pick you do the point slope form of the line, you solve for the y-intercept. All right, so you plug in a point, whichever point you want. It doesn't make any difference. Pick x1, y1. And so you put in your y1 point, you put in your slope that you've calculated right there on your graph, you put in your x1 number off your graph, so y1, x1, these are the numbers off of your graph, off of the point that you picked, all right, and then plus the ln of a. So you have a number, you have a number, you have a number, you solve for the a, the ln of a. All right, and so mathematically, then you're going to take and subtract your slope and your value x1. So you're going to have y1, and then we're going to subtract on both sides the product of your slope times x1, and that will equal to your ln of a. To get rid of the ln, you have to pick the e to the x button, and that gives you your Arrhenius frequency factor. This has the same units as K. All right, and then the K units were 1 over molarity times second. It was a second order reaction. All right, so that is how you get your Arrhenius frequency factor. All right, slope, y-intercept, that's the y-intercept. All right. All right, so then that is it. So then you write on number 6 your answer. All right, so your answer here goes on number 6 on your report sheet. Your answer here goes to number 7 on your report sheet. Make sure you put in the units. And that is how you do the report sheet for experiment 11. A lot of points are going to be on your graph. Make sure you include everything on your graph. The right answer is not necessarily, well, it's not going to be graded very harshly at all. A proper graph is going to be most of your points. If your graph looks bad, your grade's going to look bad. Make sure you have a good graph on graph paper turned in.